it was not. No, but I had my uncle, his household is one. Oh, yeah, very nice. All right. Mm-hmm. Oh. Did you get it all right? Okay, I'm going to start. Yeah. Dear Heavenly Father, we thank you for this day, and just help us to use this time wisely, Lord. In your name I pray. Amen. So their brother is at the dentist, and, well, so they're here. So I don't have your homework graded for some reason. Yeah. Yes?
Did you post the solution?
I have not posted the solution yet.
Well, I emailed you this morning, and I also didn't check. So unless you did it after. I checked it like 1 Okay.
Yes, I can definitely post the solution. I will attempt to do that right now. Yes. Oh, yes, very nice. Oh, yes. There we go. I think it should be, you should be able to get to it after class now here. Oh, there's mission 1. I was like, did I post mission 1 solution? I did. It's just at the bottom. I never. Okay, now. I guess I'll let you, well, let him run around. If he gets too out of control, I'll. Mom said to use the phone. Mom said to. So Benjamin, what do you think? Should we do class? Yeah. The ball. He's not going to say moon for you. Oh. All right, so I will continue. We are going to begin our discussion of Galois theory. AKA chapter 14 in Dummit and Foote. Right? Now, I should mention from the outset that there are a number of excellent PDFs that have been written about this, little articles. In particular, Professor Keith Conrad of University of Connecticut, he has a website where he has posted many of what he calls blurbs, and on dozens of topics. But his blurbs on Galois theory are particularly lucid and helpful, and also very much based on Dummit and Foote. So they're kind of like notes by somebody who understands Galois theory very deeply, expanding on Dummit and Foote, as if that's possible. It is possible. Dr. Conrad's blurbs are just that. So at times, as we continue on, after that Unpleasantness Friday, I may reference his blurbs from time to time because they're very useful. But I'm going to start in Dummit and Foote and pretty much just hit section 14.1 as much as I can today. Here's the definition. All right, Hannah, give him the
Over here. Ooh, look.
There we go. Okay. So here we go, definition. And see, he'll actually be fine. I'm more doing that for you guys than for him. An isomorphism, sigma, of k to k is an automorphism. Automorphism of k. All right, so like aught k, what is this? This is equal to sigma from k to k, such that sigma is isomorphism. What kind of isomorphism? Isomorphism of groups, isomorphism of vector spaces, what kind of isomorphism are we talking about here? What is K? I should tell you, huh? Field, right. So we're talking about isomorphism, field isomorphisms, right? And he also mentions that we'll write composition. Well, anyway. So that's point number one. Number two, definition here. If sigma is an automorphism of K, all right, then if X in K has sigma of X equals to X, then sigma fixes X. All right. So sigma fixes X. Oftentimes, it's not fixing a single element we're interested in. It is if we have a subset. If we have a subset f of k, and sigma of x is equal to x for all x in f, all right, then sigma fixes f. All right, so we could talk about an automorphism fixing a whole subset of a field, all right? So, given a field, does it have any automorphism? Yes?
What's the difference then between an isomorphism that fixes a field and just the identity map?
Well, that is true. Good point. If we have a field and we look at the identity map, then true. That is an automorphism of the field which fixes the entire field. That is a possibility. And that also points out my next point, which is that there's always at least one automorphism for a field, right? Because we always have the identity map. And in fact, we can prove that the set of automorphisms of a field forms a group, right? So with respect to composition of maps. The question is, how big is that group and what's its structure? And how is that related to subfields of the given field, which automorphisms in there are fixing? This is more or less the discussion we're trying to have today. He points out that if you look at observation, for a given K, the unity generates what? Prime subfield, right? So, because we can build the prime subfield by repeated addition of 1, right? And so forth. We talked about this before. And depending on whether the field has characteristic 0 or characteristic p, we're either going to get the prime subfield being what? The rational numbers, or what's the other choice? Z mod p. Oh. This is not good. He's grown disinterested in videos. Here, Benjamin. Come on. Come here we go. All right. So the prime subfield for a given field, we can always generate the prime subfield by 1, right? Do you remember this, guys? We can repeatedly add 1 and so forth.
Multiply by, so it's just adding. That's all that you do with 1 to generate the prime subfield.
Well, it's more than that. I mean, so if it's a field, then of course so you start with 1, and then that allows you to build 1, n times 1, right? Which is 1 plus 1 plus 1 plus 1. Essentially, the set n times 1 is a subset of k, which is equivalent to the integers as a ring. Let's just focus on the characteristic 0 case for the sake of discussion. So you start with that, you build that, that's a copy of the integers inside your field, whatever it is, if it's a characteristic 0 field. And then, because the field is closed under, the field is closed under division, right, since it's a field, so then you can use these to build fractions of those, right? I mean, in other words, you can take the field of fractions. This is an integral domain inside your field. You can form the field of fractions over that. That will again be a subset of k. And that field of fractions will be isomorphic to the rational numbers if your field is characteristic 0, or it'll be isomorphic to the, z mod p if your field has prime p. But one of the two of these things has to happen for any field. There's a prime subfield, all right? I'm getting way off topic here, guys. But his larger point is, what can we say about the prime subfield for an automorphism? He argues that an automorphism automatically fixes the prime subfield. If sigma is in the automorphisms of k, then sigma fixes the prime subfield. Why is that true? I mean, you don't believe it? Well, sigma of 1 is equal to 1, right? And because that's true, that means 1 is fixed. I mean, essentially by definition of ring isomorphism, right? So once you have that, it leads to everything else that's generated from 1 being fixed, just the same. I mean, to just kind of give you a big picture of it, it's something like this. If we have a fraction a over b, right, in the prime subfield, then that can be written as sigma of a times sigma of b inverse, right? But I'm assuming here a and b are in the integers, quote unquote integers of the field, whatever that is, be it a copy of z or a copy of zp, and then this is really, you know, a times sigma of 1, and then b times sigma of 1 inverse, right? But sigma of 1 is 1, so this is really a times b inverse, which is a over b. So that shows you that it fixes the prime subfield. Yeah.
So you can pull out the A and B because they're elements of the field?
No, because a and b are elements of the integers. A and b here are in the integers of the field. Well, the integral domain inside K generated by 1. And you know, up to isomorphism, that's either the integers or z mod p. But you take that and you build the ring of fractions over that. Because this K is a field, you know that's still inside K, right? And so, I mean, technically the ring of fractions is built on equivalence classes or something, but that set of equivalence classes, you can find a unique correspondence to a particular subfield of the given K, which we identify as sort of being the rational numbers in K, or the z mod p inside K, so to speak, yeah. Okay, good. Now, definition. Definition. Let K over F be an extension of fields. All right. And let ought K over F be the collection of automorphisms of K which fix F. So in terms of this brand new fangled language that we got here, all right, you could say that ought K over F is these are the F fixing automorphisms of K. All right. So immediate comment here would be that if F is prime subfield of K, then ought K over F is just equal to what? Which automorphisms fix the prime subfield? The answer is all of them. So this is just ought K again. But for more interesting fields, this isn't always the case. I mean, there can be only some of the automorphisms of a field which are fixing a particular subset of it, okay? We're going to see this as we go on here. All right. Page 2. Proposition. Is it okay if I think I can safely erase our proof of the red comment, yeah? Proposition 1, Prop 1, ought K is group under composition, and automorphisms of K fixing F form a subgroup. Of the automorphism group of K. All right. So the first claim, that's 421. I mean, we've done that before. In fact, this very well could be a homework exercise at the end of 421. It'd be a pretty good one. It was? Ah, we know. So it would be a lazy homework because I already know it works out and it's not too hard. So if we have two isomorphisms, the composition of two isomorphisms is an isomorphism, right? And so you can prove the automorphism group is a group under composition. But the second claim we should work through, right? So let's see, let sigma and beta be in the F fixing automorphisms over K, right? And let X be an element of F. Then if we look at sigma beta of X, what do we get? Sigma beta of X, right? Which is what? Well, beta is in the F fixing automorphisms, so beta of X is X, right? And sigma of X is X, so therefore sigma beta is in the automorphisms of K over F, right? Is the F fixing automorphisms of K non-empty? So what's in there? The identity map, right? I don't know, is an element of aught K over F. Let's see here. And what about inverse? Second inverse of X. Now I was like 2 years ago now. I was teaching I think it was the first time I taught 422. I got horribly stuck on this. I'm like, oh, I can't. How do you get the sigma inverses in the? It's so dumb. It's so dumb. So sigma inverse, first of all, exists, right? Because it's the inverse of an automorphism, which is an automorphism, right? So that's not the problem. But how do I? So here it is. Do you guys know how to show that sigma of X is equal to X again? No, because X here is in F, and F is not necessarily, F doesn't have to be the prime subfield. That calculation is not available here. I don't know I can build X from 1. It could be other things. Uh-huh. There's the thought I could not have when I taught this a couple years ago. And without that thought, this is very difficult. But once you have that thought, well, this is X again. Yeah. So what does this show you? Oh, and I should have said let sigma be in, so I forgot. Let sigma be an element of the F fixing automorphisms over K, yeah? I mean, I just started talking about sigma. What's sigma? You guys be like, I don't know, what are you talking about sigma, right?
Well, you already said it up there.
Oh, I just looked at that and read an alpha. What's wrong with me?
I did it first.
Oh, man. Whoa. Okay, anyway, get to the point here. We've showed that this aught K over F is closed under, under multiplication and also inversion, right? It's not empty, so by the subgroup test, right? Therefore, aught K over F is subgroup of aught K. All right, off to the races here. It's proposition 1. Great. Proposition 2 is, it's starting, where we're starting to get to something that's genuinely, I would say, interesting. Proposition 2. Let K over F be field extension. Do I need to turn the volume off on that? You got it, Hannah? Yes.
So you have the sigma inverse x equals sigma inverse sigma x equals x period. What does that next word say?
I don't know. I think it was I was writing thus, and then in my mind I changed to writing that, and it became a thut. So let's see here, which is, to my knowledge, not a word. But I'm not a Scrabble master or anything, so what would I know? K over F be a field extension, and let alpha alpha, an element of K, be algebraic. Over F, all right? Then, that's then, for any sigma, that's a sigma, in aut K over F, we have sigma alpha is root of the minimal polynomial for alpha over F. In our usual language, we have this m sub alpha comma F of sigma of alpha equals to 0. If you plug in the F-fixing automorphism acting on the root for the minimal polynomial of alpha, it also is a root. He says what this means is that the F-fixing automorphisms of K permute the roots of irreducible polynomials. All right, they permute the roots of irreducible polynomials. He says equivalently, any polynomial with coefficients in F having alpha as a root also has sigma alpha as a root. Actually, we'll prove the latter sentence. We'll prove that any polynomial in Fx having alpha as a root has sigma alpha. Now, so by the way, guys, sometimes I write sigma of alpha, sometimes I write sigma alpha. He works under the notation in chapter 14 that sigma of alpha is sigma of sigma alpha. You know, just a warning, like he doesn't always write parentheses of something. And sigma and alpha are really different things. Sigma is a permutation here. Well, it's an automorphism, whereas alpha is an element. So it's you know, I don't know. I have mixed feelings about this notation, but whatever. Has sigma alpha as a 0, as a root. Where for any sigma in the F-fixing automorphisms of K. All right? Yep.
Isn't sigma of alpha always just alpha? Or is that not true?
I didn't say alpha was in F. Alpha's in K. Sigma fixes F. So let's take that polynomial. Let's call it f of x. Let's say c0 plus c1x plus c2x squared plus dot, 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 plus cnx to the n. All right? There you go. Polynomial in f, all right? So that means the coefficients are taken from the field f, right? then let sigma be an f-fixing automorphism of K. And suppose that there exists alpha in K such that f of alpha is equal to 0. Right? Yes, Isaac. Watch out for Daniel. Continue. Isaac's like my resident narc. Let's see here. Okay, so let's look at what does f of sigma of alpha look like?
That the cameraman is doing the wrong job.
Thank you, Isaac. It was helpful. What are you doing? Getting to the marker board. You know, you could just go up to the front and crawl. It'd be faster. You know, he's just going to like pan the camera down to get, you know, footage of you anyway. That I approve of. Thank you. Okay, so in the interest of saying something more today, C0 plus C1 sigma of alpha plus C2 sigma of alpha squared, right? Plus dot 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 plus Cn sigma of alpha to the n power, all right? But the thing is, we can rewrite this as what? This is really sigma of C naught, sigma of C1 times sigma of alpha, sigma of C2 times sigma of alpha squared, right? Sigma of plus dot 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 sigma of Cn times sigma of alpha to the n. Do you know what I did there? Sigma of alpha to the jth fold power is equal to sigma of alpha to the j, right? That's a law of exponents for a homomorphism. So I'm using that for j equals to 2 through n to bring the power from outside to inside, which is important because then the next step, I'll use the homomorphism property again, multiplicative. So I got like sigma of C0, sigma of C1 alpha, sigma of C2 alpha squared. So we have to use the fact that we're looking at a homomorphism of rings, right? So it does a lot of things at once, right? It preserves addition, it preserves multiplication. So, you know, a lot of toys to play with here. And then, what do I got? At that. What's inside the parentheses now? What? 0. Why is it 0 though? That is, right, that is f of alpha. And what is sigma of 0? It is 0, right? So that proves that if we have a polynomial in f, which has a 0 alpha, all right? Alpha does not have to be an f, right? Alpha could be outside of the field. It could be, you know, it's in some extension field generally. Then, if you pick an f-fixing automorphism of K, right, where the again the root alpha is in K, then it follows that sigma of alpha is also a root to the polynomial, which justifies the claim that an f-fixing automorphism of K permutes the roots of polynomials. It takes roots to roots, yeah? this, I don't know, this is one of those calculations that it's just, it says something really, really cool, and yet it's a pretty easy calculation too, right? It's not that bad. And this is the heart of Galois theory, is this observation that permutations of the roots of polynomials are interesting and something we can do something with. Don't humor them. They're going to be writing something anti-math, I'm sure. Let's see here. It's in their nature. Where was I? Ah, yes. Okay. So some examples. Number one, if we look at k equals to q adjoin the square root of 2, all right, then if we look at tau in the automorphisms of q adjoin the square root of 2, all right, well, notice that that's already the what? It automatically fixes q, right? Because q is the prime subfield of q adjoin root 2, right? Because it's a characteristic zero field. And he says the following. He says then, what? Guys, go sit down, please.
Bye-bye.
Bye, yeah. Sit down. To get to be a certain age. Let's see here. Then tau of the square root of 2 is what? So this is the start of a long conversation in here about how automorphisms behave for fields. Like, that's something you guys don't have a lot of background in, but it's something we're going to learn. All right? And so the essential story is that automorphisms have to take elements to sort of their own kind. All right? So in the field q adjoin the square root of 2, there's a square root of 2, and there's one other thing like it, which is, right, negative the square root of 2. So if you look at it, and what are we using? Why, that's actually the thing we just proved, right? Why is that? It's not directly the thing we proved, right? If you think about f of x equal to x squared minus 2, right? That polynomial has the square root of 2 as a 0, right? And if tau is a q-fixing automorphism of q adjoin root 2, that means it has to send a 0 of f of x to another 0 of f of x. Well, square root of 2 is a 0 of f of x. So the choices are you either send it to itself or you send it to minus itself. Them's your choices. So this has to be plus or minus the square root of 2. So those possibilities define possible automorphisms. Do you see why that is? So we can have tau 1, which is defined by the square root of 2 equals the square root of 2. Or we can have tau 2, which is defined by the square root of 2 equals minus the square root of 2. My claim, hey, no talking. Come on, guys. Should I make the punishment? Do you guys have any ideas? How should I punish them? Any suggestions? Many of you future parents, probably. Statistically speaking, it's likely. Punish them by letting class out early. That is a very, very hyperbolic punishment. I don't understand that. You're going to have to. Make them take.
Give us a good grade.
Make them take your test and give you a good grade.
Oh, they're really getting it now.
And give them a test
Oh.
that you would give us, and give us a test that you would give them.
Oh, I like. You take.
Bethany Benjamin's test.
So, I'm telling you guys that what I wrote on the board defines tau 1 and tau 2. How is that reasonable? I mean, tau 1 and tau 2 are supposed to be automorphisms of Q adjoin root 2. How does that alone define tau 1 and tau 2? Like, you tell me what's the formula for tau 1 of what's a typical thing in that? A plus B root 2, right? So what's the formula here? I mean, if it's an automorphism, assumably this would be tau 1 of A plus, tau 1 of B square root of 2, right? But how is that, unambiguously defined already by the structure here?
That's just A plus B tau 1 square root of 2, right?
So you said tau 1 of A is A, right? And this is plus tau 1 of B times tau 1 of the square root of 2. But what's tau 1 of B? It's B. Because what? Because any automorphism of Q adjoin root 2 fixes the prime subfield. So whenever you find something in the prime subfield of a field that you're working in, and you're working with an automorphism, you can just pull it out. I mean, it's fixed. This is the thing we should remember. And tau 1 of root 2, well, we already defined that to be square root of 2 here. So that is why telling you what happens to square root of 2 tells you what happens everywhere. More generally speaking, if we have a field which is, so like a primitive field, will be fixed by what happens to the generator. If we have multiple generators like Q adjoin square root of 2, comma square root of 3, we'll need to say what happens to both root 2 and root 3. All right? Where do they go? That will kind of describe an automorphism. That's the calculations in this section that we're going to have to understand. So that's tau 1. And so by the same token, tau 2 is essentially, it's not complex conjugation, but it's sort of conjugation, right? Like you change root 2, you change 2 to minus root 2. So you can tell me though, so tau 1 times tau 1 is what? It's 1, right? I mean, it's quote unquote 1. It's the identity automorphism. It's the identity on Q adjoin root 2, is it not? Because if you do it, I mean, tau 1 is, I'm an idiot here. Tau 1 is the identity, right? Sorry. I mean, this is true, but tau 2, on the other hand, this is more interesting. Tau 2 times tau 2 is also tau 1, right? I mean, it's the identity. So if you look at it, what I'm saying is that the automorphism group of Q adjoin root 2 over Q, just for the sake of, making it look like that, it's what? It's the set containing the identity and basically tau, where tau of root 2 is minus root 2, I mean, this is the automorphism group of Q adjoin root 2. They're just two things in it. Hi, Isaac. I will foolishly attempt to do one more example today. Example 2 is to look at K equal to Q adjoin the cube root of 2. All right? And he says, suppose tau is an automorphism of K over Q, right? Which, of course, would just be an automorphism of K, right? Because Q is the prime subfield again. So notice, again, f of x equal to x cubed minus 2 has the cube root of 2 as 0, right? So let's see here how to say this. If we look at tau, so he says this. He says tau is completely determined on its action of the. So here's what he writes down a formula here, which is useful to write down: a plus b times the cube root of 2 plus c times the cube root of 2 squared. That's like a generic element. So what would tau do to that? Does nothing to a. It does nothing to b, but we got to figure out what tau does to the cube root of 2, right? And then over here, you're going to have tau acting on the cube root of 2 squared, right? That's why if you tell me what tau does to the cube root of 2, it completely determines what tau is, right? So tau of the cube root of 2, this alone is enough to define tau. But what is our proposition 2 telling us? It tells us that it does what? What does tau have to do? It's a q-fixing automorphism of q adjoins cube root of 3. Where can tau send a root of x cubed minus 2? It has to send it, you say only to itself, but the logic of that, what I was fishing for was it has to send to another 0 of x cubed minus 2, right? There are 3 zeros of x cubed minus 2, but 2 of them come in a conjugate pair, neither of which is in k. So those are not options, because we cannot define tau of something in k to be something outside of k. That wouldn't be an automorphism of k. So it certainly wouldn't be a q-fixing automorphism of k. So the only choice is cube root of 2 again. The only choice is the cube root of 2 again. And therefore, what's the automorphism group of k which fixes q? It's the trivial group, right? It just has the identity map in it. It is not an accident that q adjoin the square root of 2 is a splitting field for x squared minus 2, whereas x cubed minus 2 does not have q adjoin cube root of 2 as a splitting field, right? X cubed minus 2 is not split in k, right? Those other two factors require something else. There's a little bit more to what I'm saying. I'm saying there's something about this being the identity which is connected to this observation I'm making. And there's something about this group being as large as the splitting field. The splitting field is like, two-dimensional. The group got two things in it. Or I should say it's a degree 2 extension. I'm being very vague right now, but these things become precise in section 14.2 when we learn the fundamental theorem of Galois theory, which connects the automorphism group of k fixing a subfield and field extensions, which are quote-unquote Galois. So we need to, that's the next thing up, is we're going to define what does it mean for an extension of fields to be Galois. What is a Galois extension? But we'll save that for after the test. I think this is a good place to stop. So.